Hi, in this video I will be walking through question 1 and question 2 for Unit 3 paper for January 2021. So it's the newest paper that I think I can get. So far, yeah, obviously because the summer papers are not going on, and yeah, this is for IEL and Excel chemistry, by the way. Okay, so let's just start. So if you look at question 1, let's start reading first. A student was provided with 5 test tubes labeled A, B, C, and D, A, B, C, D, and E, A, B, C, D, and E, each containing a colorless aqueous solution. The 5 solutions were known to be barium chloride, nitric acid, potassium bromide, silver nitrate, and sodium carbonate. The student carried out a series of tests to identify which test tube contained which solution. So obviously you will be testing the cations and anions, the positive ions and negative ions, okay? The student tested each solution using universal indicator paper. The solution A turned the paper red. Identify solution A. So before we actually look at the first question, look at how to solve that question, it's tests. So we will be testing for the cations and anions. So I started off by just separating the ions inside those 5 solutions. Okay, so if you have an aqueous solution of barium chloride, obviously you're going to have barium 2+ in there and chloride ions in there. Nitric acid is going to be fully dissociated into H+ and nitrate ions, NO3-. And potassium bromide is going to have K+, Br- bromide ions, silver nitrate, Ag+, and nitrate ions. And for sodium carbonate, you're going to have your sodium ions and carbonate ions. Okay, so the first question, it says the universal indicator paper have turned red, right? And we know that for red is going to be, indicating a very low pH. So therefore it has to be an acid. And if you look at your 5 choices, you only have one acid, which is nitric acid. So therefore your only answer is going to be nitric acid, okay? So that was easy breezy. And the second question, that the student mixed 1 centimeter cube of solution A separately, so acid, with 1 centimeter cube of each of the other solutions. And there was no change for 3 of the mixtures, but effervescence was observed when solution A was added to solution C. Identify solution C. So solution A is HNO3, and we know this equation, right, from GCSEs as well. Acid and metal carbonate, when they meet up, you get carbon dioxide, water, and a salt, which is basically the ionic compound that you get. And so if the acid was nitric acid, you will have to look for the metal carbonate, right? Oh, and this reaction, by the way, happens because this is a neutralization reaction. Okay, so carbonate, they accept protons acting as a base, and that's why there is a reaction between them. And if you look at your options, you only have sodium carbonate and no other carbonates, so it is pretty straightforward. This one, solution C, has to be sodium carbonate, okay? And it says, write an ionic equation for the reaction between solution A and solution C. Include state symbols. You must include state symbols for ionic equations because we know that only aqueous ions can be separated into ions, okay? So I firstly started off, if you already know the ionic equations, how they go, because this is an acid-base neutralization reaction and it's between just H+ and carbonate ions, you can obviously write it down, but just to make sure that you know how to construct ionic equations from full ionic equations, I'm going to go through how to do that. So first of all, I wrote the full equation of the reaction between nitric acid and sodium carbonate, okay? So if you have nitric acid and sodium carbonate, you get a carbon dioxide, water, and 2 moles of sodium nitrate. Okay, so that is our metal, the ionic compound, the salt. Okay, so we can separate the aqueous substances into their ions. Okay, you cannot separate anything that is solid, gas, or liquid. Okay, keep that in mind. So if I basically separate HNO3 aqueous, Na2CO3 aqueous, and NaNO3 aqueous, I get 2H plus over here, 2NO3 minus, 2Na plus, carbon and the carbonate ions, and we have the sodium ion and the nitrate ion over here as well. Then what we can do is to cross out these spectator ions. So if you have the same ions on the reactant sides and the product side, obviously you can cancel them out, right? So if I do that, I am left with the ionic equation, which is 2H plus aqueous, so state symbol, very important, and we have the carbonate ion aqueous, and we have carbon dioxide and liquid being formed. Okay, so that is our ionic equation. So I wanted to discuss a little bit more about some common ionic equations. So we have over here two neutralization reactions, H plus aqueous, OH minus aqueous, forming water, liquid. And we have H plus aqueous with a hydrogen carbonate ion. And that is going to give us H2O and carbon dioxide. So this looks quite similar to the ionic equation that we just looked at over here, but it's not the carbonate ion, we are using the hydrogen carbonate ion. Okay, so example solutions could be HCl and NaOH for the first ionic equation, and for the second ionic equation it could be HCl and sodium hydrogen carbonate. Okay, yeah, so just keep in mind these common ionic equations, and let's move on to the next question. The student then mixed 1 centimeter cubed samples of the remaining solutions as shown in table 1. So they mixed B and D and they saw no change. B and E, cream precipitate. D and E they gave us a white precipitate. So identify the 3 remaining solutions. So first thing that comes into my head, and that probably should come into your head as well, is if you see cream and white together, then it's kind of, white, cream, yellow, those precipitates, it's CaGCl, AgBr, and AgI. So AgCl, silver chloride precipitates are white, silver bromide precipitates are cream, silver iodide precipitates are yellow, okay? So, we are basically trying to test for halide ions using silver nitrate, okay? So from B, D, and E, we need a silver nitrate, okay? So out of the 3, one has to be a silver nitrate solution, which was in one of our choices. So yeah, let's continue. So we also have, if we're testing for halides, we obviously need the solutions that contain the halides, right? And we have KBr, potassium bromide, and barium chloride with halide ions from our options, okay? So from B, D, and E, we know that there has to be AgNO3, KBr, and barium chloride, okay? And also because we have used up HNO3 and sodium carbonate, yeah, those are already used, so we're just left with those 3, right? Okay, so first of all, if a cream precipitate was there, then either B or E has to be a KBr, right? Because the cream precipitate is AgBr that has formed, and that can form from potassium bromide and silver nitrate. And for D and E, a white precipitate, which is AgCl, has formed, and that can only form from AgNO3 and barium chloride, okay? So, and we can also see that they have E in common, so probably E is AgNO3, but also another evidence that E is going to be AgNO3 is because B and D, they gave us no change, they don't react together, because KBr and barium chloride, these are just neutral salts, okay? These are just neutral ionic solutions. So K plus and Ba2 plus, bromide ions and chloride ions, they're just gonna hang around in the solution, they're not going to react, okay? So B and D are going to be KBr and barium chloride, and therefore we know that for sure solution E has to be silver nitrate, okay? And then it's easy now, so the E is not a choice, and B has to be the one that gives the bromide ion, so it has to be KBr, and D has to be barium chloride, okay? So I hope this was pretty clear, piecing all the evidences together. Oops, that's my alarm. So B, 3 of the cations in the compounds in A can be identified using flame tests. So flame tests, right? So before even, thinking about anything, some of the flame colors that you have to memorize are, first of all, we have barium, Ba2+, it burns with a pale green flame, and potassium is lilac, magnesium is just white or colorless. Sometimes people say white, sometimes people say colorless, but just go with colorless, it's safer. Most mark schemes say colorless in my experience. And we have sodium, which is yellow, like sodium lights, and we have the reds. So for calcium, strontium, and lithium, they're all red. Yeah, technically you're not wrong if you just say red for all the 3, but basically calcium is more like orange red, strontium is red, and lithium is going to be crimson red. Okay, so I hope you don't get confused with the reds. Anyways, so the 3 cations in the compounds. So we had in our compounds barium, potassium, and sodium. Okay, so if you, barium chloride, we had barium chloride from our choices. We had potassium bromide and sodium carbonate. So if you just label down barium 2+ burns with a pale green flame, potassium burns with a lilac flame, and sodium burns with a yellow flame. So this is just memorizing. You have to memorize your flame tests, okay? Number 2 now, sodium hydroxide solution reacts with carbon dioxide in the air and should be standardized before use. Ethanoic acid may be used for the standardization. So that first 2 sentences is not really extremely important, so it's just extra detail, I guess. A standard solution of ethanoic acid is prepared. So first of all, they dissolved 2.4 grams of solid ethanoic acid in 100 centimeter cube of deionized water in a beaker, which is the same thing as distilled water. So there are no ions inside the water. It's just purely H2O liquid. The solution is transferred into a 250 centimeter cube volumetric flask and made up to the mark with deionized water. So basically, this 2.4 grams of solid is inside 250 centimeters cubed of H2O liquid. Okay, so it's dissolved completely inside 250 centimeters cubed. That's a total volume. Okay, give a possible reason why any solution remaining in the beaker is washed into the volumetric flask before making up to the mark. So I just wanted to draw out what is happening there. So first of all, you put the ethanoic acid solid inside a little bit of water inside a beaker, and then you're going to dissolve it. Okay, so that's it. It won't actually look like that, but I just wanted to express that it's dissolved. You won't see these particles if it's dissolved, obviously. So and then you're going to transfer it. This is the volumetric flask. I know it's not the best drawing, but and this is a funnel. Obviously, you should use a funnel so that you don't lose any of the ethanoic acid that's dissolved in the water, okay? And, because if you spill it, you don't want to do that. And after you have transferred that solution in the beaker into the volumetric flask, you might have some droplets of the solution remaining on the bottom or on the walls of the beaker, okay? So you have to wash down the walls and obviously the bottom and transfer it again into that volumetric flask so that you can ensure that you have every bit of ethanoic acid inside the volumetric flask, okay, not in the beaker. So yeah, the drops remaining on the wall of the beaker may contain dissolved ethanoic acid. Okay, so you don't want to leave anything behind. Transferring the washings ensure that all the dissolved acid is in the volumetric flask, okay, so that you can have a fixed, known concentration of the ethanoic acid solution. All right, so calculate the concentration of this standard solution of ethanoic acid in mole per dm cubed. Give your answer to an appropriate number of significant figures. Okay, so we're given the total volume, which is 250 centimeter cubed, and we are also given the mass of ethanoic acid, which was 2.4 grams, right? So with that in mind, you can't actually do it in just one formula, right? We need two formulas. Mole equals volume times concentration, and mass is equal to molar mass times the number of moles. I hope you know this formula already by, from GCSEs. And I, first of all, rearranged this formula over here so that I can equate it to the number of moles, okay? So number of moles is equal to mass over molar mass. And you can equate these two equations, and you can just put in everything that you know from the question. They give you three variables. If you have this formula, so mass over molar mass equal to volume times concentration, this is what you need, right? And the total volume was 250 centimeter cubed, which is you need to divide it by 1000, obviously, to change it into decimeters cubed, because the concentrations unit is mole per decimeters cubed, right? Do not forget converting this cm cubed into dm cubed, okay? And the mass of the acid, again, was 2.4 grams, and the molar mass of the acid is given, or else you can also calculate it, right? It's 12 times 2 plus 16 plus 4 and plus 2 from 2 hydrogens. Yeah, so that is going to go under there. And if you basically calculate it, you should get 0.106 recurring, and you can round that up to 0.107 mole per dm cubed. So with the significant figures over here, I used 3 significant figures because the question also used 3 significant figures, okay? So that is kind of the more sensible thing to do. Right? Yeah, so the next question. A different standard solution of ethanoic acid is used to determine the concentration of a sodium hydroxide solution J. Okay, so we're not using that 0.107 mole per dm cubed solution of ethanoic acid. We're using something else, okay? So yeah, step 1, a burette is rinsed with deionized water, distilled water. The burette is then rinsed with 0.09 mole per dm cubed ethanoic acid and filled with this acid solution as well, okay? A pipette is used to transfer 25 centimeters cubed portions of solution J to conical flasks. So I hope you know how a pipette looks like. I drew one. You will see, but yeah, if you don't know exactly how they all look like, then I highly recommend watching a video on it. Okay, the portions are titrated with the ethanoic acid solution using phenolphthalein indicator. So that's phenolphthalein indicator is what they used, and that's why I colored this pink, because inside the conical flask is sodium hydroxide, and phenolphthalein is pink when it's an alkaline solution, and obviously sodium hydroxide is alkaline because of the hydroxide ions acting as a base. Yeah, explain why the burette is rinsed with ethanoic acid solution in step 2. So yeah, over here, this burette has to be rinsed with ethanoic acid before we actually do the titration. That is because if there is water remaining in the burette, because before we rinsed it with ethanoic acid, we rinsed it with deionized water, right? If we have some water remaining in that burette, the acid solution that we pour into the burette is going to be diluted, okay? The concentration, therefore, will be lower than 0.09 mole per dm cubed, and that is going to affect the titer, right? So if the concentration is less, that means we have less number of moles of the acid inside the burette than expected, which means that we're going to need more of the acid to neutralize the same 25 centimeter cubed of sodium hydroxide. Okay, so yeah, it's going to lead to errors. All right. The diagram shows how the student read the filled pipette in step 3. Identify the 2 mistakes the student made. So first of all, what I can see is the eye position, right? The eye position has to be at level with the pipette mark, okay? Because if you're looking at from below, then it's going to look like the mark is a little bit higher than, the meniscus. Meniscus is the bottom of that little curve of that solution. It's going to look like it's a little bit higher than it actually is. And conversely, if you are looking at downwards from a elevated position, then you're gonna look, the meniscus is going to look like it's going to be lower than where it actually is, okay? So therefore, it's very important that the eye should be at level with the pipette mark. That is to, avoid parallax errors, okay? It's called parallax errors when when your eye position is not level. And the second error is that the meniscus, which is the bottom of the curve of that solution, that must touch the pipette mark like this. Okay, so this is going to actually, be less than 25 centimeter cubed. Okay, yeah, those are the 2 errors. And the student completely emptied the pipette for each transfer in step 3. Explain the effect on the titer of completely emptying the pipette rather than leaving a small amount of solution in the tip. Okay, so yeah, that's how a pipette looks like, and that's the pipette mark where it's indicating that it's 25 centimeter cubed in there. And yeah, and if you look at over here, it says 25 centimeter cubed plus minus 0.06, right? Yeah, that is, no, that's the absolute error, actually. Just never mind. Yeah, that's the pipette. And pipettes are actually designed so that there is a little bit of solution left on the tip of the pipette. So as you can see, that little bit, X centimeter cubed, it's a very, very small amount, but yeah, it's designed so that there's a little bit left, okay? If you fill the pipette up to the mark, it actually has 25 plus X centimeter cubed, okay, of the solution. So, but if you basically release that solution from the pipette, then it's going to just release 25 centimeter cubed, and that X centimeter cubed is going to just remain in that pipette, okay? So if you blow that out, you're basically putting in more than 25 centimeter cubed. So you would have a little bit more sodium hydroxide inside the conical flask. So yeah, there will be a slightly larger volume of sodium hydroxide than 25 centimeter cubed in the conical flask. So the volume of acid required to neutralize that will also become larger, right? So therefore your titer values are going to increase, and it's going to be an inaccurate titer value. So next it says, state the color change in the conical flask at the end point. So at the end point is where the neutralization reaction occurs, right? Meaning that all your OH minus ions are going to be neutralized with H plus, and you get H2O. Phenolphthalein again is pink in alkaline solutions and colorless in acidic solutions, okay? And inside the conical flask, we know that there was sodium hydroxide, which is a base, which is alkaline. So the color change is going to be from pink inside the conical flask to colorless, okay? That was pretty easy, and the titration results are shown below. You just have to calculate the titers from, subtracting from the final reading, the initial reading. So yeah, just do that. 25.05, 24.60, 24.50. There are some people who don't write this 0 over here, but it's very important to be consistent with your data points, okay? yeah, the decimal points should be all consistent. So we have the final and initial readings all up to 2 decimal places, right? So I want you to write 2 decimal places for your titer values as well, okay? Be consistent with your data. And titers used in calculation of the mean. So you need to use concordant results, okay? So 25 over here is a lot, further away from these 2 values. These 2 values are they're concordant because they're only plus minus 0.1 centimeters cubed away from each other, whereas 25 is a little bit more. There's a little bit of a bigger difference. So these are your accurate titers. This is just like a trial, okay, to get to the accurate titers. So calculating the mean titer, obviously you're gonna just use your accurate titers and add them up, divide by 2, and you should get 24.55 centimeters cubed for your mean titer. And lastly, we have our calculation question for question 2. Calculate the concentration of sodium hydroxide solution in mole per dm cubed. The equation for the titration is, so you have this equation, and yeah, the Ethanoic acid solution, this was from a standard solution, right? So we know the concentration, which was 0.0900, and we also calculated the mean titer, so the volume of this ethanoic acid solution that we used to titrate the sodium hydroxide. And we know that the sodium hydroxide solution that we used inside the conical flask was 25 centimeter cubed, okay? So with that all in mind, let's start. Yeah, again, 24.55 centimeter cubed used, that's our mean titer, and the concentration was given in the question, and therefore you can obviously work out the number of moles, right? Mole equals volume times concentration. So volume, again, you need to divide it by 1,000 because this is in centimeters cubed, and the concentration's unit is dm cubed, right? So we need to change it into dm cubed by dividing it by 1,000 and times it by 0.09, then you get the number of mole of the ethanoic acid that you used. And then if you look at the equation over here, the stoichiometric ratio between the ethanoic acid and the sodium hydroxide is 1 to 2, okay? Which means that if you had 1 mole of ethanoic acid, you would need 2 moles of sodium hydroxide for complete neutralization. But over here, so that's the general ratio, but you actually have this amount of mole, this number of mole of ethanoic acid, right? So you just need to times that by 2 to get the number of mole of sodium hydroxide that you actually had in the conical flask, okay? So that is the number of mole of sodium hydroxide that was inside a 25 centimeters cubed volume in the conical flask, right? And 25 cm cubed, if you change it into decimeters cubed, then it's 0.025 dm cubed. And obviously concentration is the number of mole over volume. And so the number of mole of sodium hydroxide that you just calculated using the stoichiometric ratio is going to be on top. And on your denominator, you have your volume, which is in dm cubed, 0.025, and then you can calculate your concentration. So you get 0.1676, and I change it into 3 decimal places, which kind of looked sensible. So 0.177 mole per dm cubed should be your correct answer. So that was it for question 1 and 2, and I'll hopefully work on question 3 and 4 fairly soon, so that I can upload the video fairly soon. But making these it kind of takes long, but I mean, please be patient with me. Thank you.